We will now show that a monotonic function on any finite interval is almost everywhere differentiable. Okay, so let f a b to r given measurable function. So if x belongs to the open interval AB, we can define the following four quantities. They are all well defined because, as you can see, this is nothing but lim sup h going to 0, h decreasing to 0 rather, f of x plus h minus f of x by h. Then d minus f x is equal to lim sup h going to 0 fx minus f of x minus h by h. Then d sub plus f of x equals lim inf h decreasing to 0 f of x plus h minus f of x by h, and d sub minus fx equals lim inf f of x minus f of x minus h by h. Okay, so then you, for instance, you have some obvious inequalities. The d sup minus sup plus f of x is lim sup of something, so correspondingly it's greater or equal to d sub plus f of x, and d sup minus f of x is greater or equal to d sub minus f of x for all x. Now f is differentiable at x if and only if d plus fx equals d minus fx equals d sub plus fx equals d sub minus fx, and that's obvious. Okay. So that's clear because you should have the limits of h going to 0 on both sides should exist, and they should both be equal, which is exactly saying the lim sup equals lim inf in each case, and then that all of them are equal. So f is differentiable almost everywhere in AB if f dash x exists, x in AB, f dash x exists at almost, or rather for almost every x in AB. That means except on a set of measure 0 is. And what is f dash x? This common value is called f dash x, derivative of f. Okay, so now we sketch the proof of this important theorem. I say sketch, proof is more or less complete, but there will be little points which need to be checked, which can be done easily. It's a time consuming process to prove the entire thing in full detail, and therefore I will give almost all the steps necessary, and so I just call it a sketch of a proof. So theorem f a b to r, monotonic increasing function. Increasing real valued measurable function. Then f is differentiable almost everywhere in AB. The derivative f dash is measurable, and integral over AB f dash dm1 is less than or equal to fb minus fa. So you see, usually in the fundamental theorem of calculus, we would have said integral f dash equal to fb minus fa. We already saw that it's not possible, and in fact the Cantor function, which is a monotonic increasing function, differentiable almost everywhere at all the flat points of on the complement of the Cantor set, f dash was 0 but fb minus fa was 1. So strict inequality can occur, and this is the best result one can say, but this is always true for every monotonic increasing function. Okay, so proof. Step 1. So you consider the set E equal to set of all x in AB such that d plus of x is strictly bigger than d sub minus of x, for example. Okay, so we will show m1 of E is 0. This is all measurable sets because all these quotients are all measurable functions, and therefore now similarly we can treat sets involving inequality between any pair of one-sided derivatives so that any pair one is unequal, then that set of measures 0, and you have a finite collection of such sets, and therefore on a complement of that set of measures 0, all the 4 one-sided derivatives are the same, and therefore the function will be differentiable. Okay, so we can write E equals union E RS, where R and S are rational and R is bigger than S. Okay, now this is countable because rationals are countable, and therefore you have enough to show m1 of ERS equal to 0. Oh, I didn't tell you what ER is. So ERS is equal to set of all x in AB such that d plus fx is greater than R, which is greater than S, which is greater than d sub minus fx. Okay. So let M equals the measure of ERS to show M equals 0. Okay. So let epsilon greater than 0 arbitrarily. There exists U open, U containing ERS, and M1 of U can be less than M plus epsilon. So this is a little better than this. We have already shown this. Given a measurable set, you can always find an open set. The two of here everything is contained in AB, so it's finite measure, and therefore you have that this is like this. Okay. So let X belong to ERS. So D sub minus Fx is less than S. This implies for all H sufficiently small, X minus H X is contained in U, and f of x minus f of x minus h is less than S times h. Because what is D minus? is f of x minus h by h lim inf, and that is less than s. Therefore, if you apply the meaning of lim inf, then you can show that for h sufficiently small, f of x minus h is less than sh. So, the collection of all such closed intervals is a Vitali covering, because given any x, I can find a sufficiently small s like this of ERS. So, by Vitali covering lemma, there exists a disjoint collection I1 In such that the interiors of these intervals covers a set A of measure of such that mu star of A is greater than m minus epsilon. Now, what is this? Vitali covering lemma says you can cover it by disjoint intervals, and the portion which is uncovered is less than epsilon. So, if the portion uncovered is less than epsilon, then the portion covered must be bigger than m minus epsilon, because m is a measure of that set. And I said interiors of these intervals because I am going to further work with derivatives and so on, and it doesn't matter, as we said, whether we had closed intervals or open intervals, the endpoints contribute nothing to the measure. Okay. Now you take ik equals xk minus hk, okay, 1 less than equal to k less than equal to n. Then what do you know? Sigma k equals 1 to n, f of xk minus f of xk minus hk coming from here is therefore less than s times sigma k equals 1 to n hk, but these are disjoint intervals all contained in U, and therefore this is less than s times measure of U, which is s less than s times m plus epsilon. Now let y belong to A. A is a set which is covered by all these I1, I2,Ins. Now then, for h dash sufficiently small, we have y plus h dash contained in U is in fact contained in some ik for some 1 less than equal to k less than equal to n, and it's in ERS. Remember, ERS means d plus is bigger than r, d minus is less than s. So, and you have f of y plus h minus fy is greater than r times h. H dash y plus h dash minus fy is greater than this. So again, such intervals form a Vitali covering of A, and so there exists a finite collection J1 Jm of such intervals, finite disjoint collection of such intervals covering a set B contained in A, and mu star B is greater than m minus 2 epsilon. So if you take Jk is equal to Yk plus Hk dash, then you have sigma I equals 1 to m f of yi plus hi dash minus f of yi is greater than r times sigma I equals 1 to m hi dash, and that is bigger than r times m minus 2 epsilon, because all these cover B and B itself has bigger measure than this, and therefore this is measure is okay. Now each J I is contained in some Ik, and F is monotonic increasing. Therefore, f of yi plus hi dash minus f of yi. So there is a difference of 2 points, values at 2 points inside the bigger one. So that is f of xk minus f of xk minus hk. Now this interval contains this interval, and therefore this has to be bigger. So adding all these things, for each term here you have a term there, and therefore you have sigma I equals 1 to m f of yi plus hi dash minus f of yi is less than or equal to sigma j equals 1 to n f of xj minus f of xj minus hj. And this is less than s into m plus epsilon, and this one is bigger than r into m minus 2 epsilon. Now epsilon arbitrary implies mr is less than or equal to sm ms, but r is bigger than s, so this implies m equal to 0. So that is mu of ers equal to 0, sorry, m1 implies m1 of E is 0, and from then we can deduce, and that will imply finally similarly other sets, and this implies F is differentiable almost everywhere. Okay, so now step 2, we have to show the inequality for that integral there. So you take fx equal to fb for all x bigger than or equal to b. and define Gn of x. We need to do that only to define the following function. Gn of x is f of x plus 1 by n minus f of x by 1 by n. So I will write this as n times f of x plus 1 by n minus f of x. So this is clearly Gn is measurable, and because its f is monotonic increasing, this is also greater than or equal to 0. So f is differentiable almost everywhere. That means f dash exists almost everywhere, and Gn must therefore converge to f dash wherever it is defined. So that means Gn converges to f dash almost everywhere. Now Lebesgue measure is complete. This implies that f dash is measurable. So we have seen an example of an incomplete, in the case of incomplete measure spaces, then if you have a sequence of measurable functions, then the limit need not be measurable. But if the space is complete, there is no problem. We have seen that also, and therefore you have that if you have a sequence of measurable functions converging to a function, so the function is itself measurable. So by Fatou's lemma, because all the Gn's are non-negative, okay, so Gn non-negative, Gn goes to f dash almost everywhere, and therefore by Fatou's lemma you have that integral AB f dash dm1 is less than or equal to lim inf n tending to infinity integral Gn dm1 of over AB. So let us compute integral AB Gn dm1. What is Gn? Gn is f of x plus 1 by n minus f of x by 1 by n. So this will be n times integral over AB f of x plus 1 by n dm1 minus integral over AB f of x dm1x, let me write dmx. And we have already done this exercise. This is equal to n times integral a plus 1 by n b plus 1 by n f dm1 minus integral ab f dm1. So you have a b, a plus 1 by n, b plus 1 by n. And therefore, if you take the difference of these two sets, this is equal to, so this portion is gone, this portion is there, and then you only have the middle portion here. Now in this portion the function is fixed. This portion goes, in this portion the function is fixed, and therefore that is equal to fb. So you will just get fb minus n times integral a to a plus 1 by n f dm1. So the Fatou lemma result now comes integral ab f dash dm1 is less than or equal to FB lim inf of this, so FB minus lim sup n tending to infinity n times integral a to a plus 1 by n f dm1. But f is monotonic increasing, so fx is greater or equal to fa for all x in a plus 1 by n. So this integral can be bounded below by f of a, since there is a n here, f of a into 1 by n into n, and therefore lim sup will be minus, so this is less than or equal to fb minus fa, because this quantity is bigger than or equal to f of a, and therefore lim sup will be bigger than fa, minus lim sup will be less than minus fa, and that completes the proof of this theorem. Okay, so this completes the proof that all monotonic functions are differentiable almost everywhere. So next time we'll see another class of functions which are differentiable almost everywhere, which come out of monotonic functions.